So last couple of days we've been, last couple of days we've been doing a lot of Newton's second law, like teaching. Like there's been a lot of, okay, here's the situation, here's the situation, here's the situation. We haven't had a lot of chance to just sit down and practice a few kind of basic problems. So rather than inundate you further with the still huge amount of different situations that could be applied to Newton's second law, or that Newton's second law applies to, I want to have you guys work on some more like kind of basic Newton's second law problems just to kind of get the hang of how they work. Okay, so we're going to work on this first worksheet here. Okay, it's on page 2 of the Dynamics worksheet booklet on Google Classroom, so you can find it there. Okay, these ones are all quite basic. Like they're like what we talked about the first day. They're basically just F equals m times a. They may involve you having to use an acceleration formula in order to get a. There's not going to be a lot of vector sum of all forces kind of stuff, okay, until you get a little bit further along, right? But the first few are all pretty basic, okay, just to kind of get you a feel for how these work, what they sound like when you read them, okay, things like that. So just a little bit of practice. Then I'm going to go into a little bit more stuff about systems, okay? We'll talk about pulleys a little bit later on today, which really isn't a whole lot different than the sliding blocks that were attached that we were talking about yesterday. It's just a different type of situation, but the same rules apply. So we'll get to that a little bit later on. And I'm hoping that by the end of class, maybe we'll be looking at inclined planes. And if not, we'll start those tomorrow. Okay, so just want you working on page 2 here from your digital workbook, starting with question number 1, which is about as easy as they get. Okay, and just kind of working through those. And there's a couple there that I'll probably do along the way, but if you have requests, I take requests, okay, and we can go through any ones that are giving you trouble as you go. All right? Yeah, I'll have a quiz tomorrow. Yes, I won't be joking tomorrow when I say it. Okay, so in number 6, what we have is the mass of the car. Okay, it's 1.08 times 10 to the 3 kilograms, so 1,080 kilograms. Okay, and it says it accelerates from rest to for 12 seconds. Okay, during this time, the car travels 132 meters north. Right? What's the net force acting on the car? All right, so I need to get F net. Right? They don't mention any of the forces acting on the car, so I can't get that using sum of all forces. There's just no way. But I can get it using mass times acceleration because I have the mass, and because I have VI, T, and D, I can calculate the acceleration of the vehicle using this formula. Okay, because VI is 0, I can cancel this part off, and I just need to manipulate for A. So I'm going to divide both sides by half of T squared. Okay, that'll leave me with A, so we'll have 132 divided by 1/2 times 12 squared, okay, and that should get us, sorry, I forgot to fire up the calculator. I'm sorry, 132 divided by 0.5 times 12 squared. All right, so our acceleration is 1.8 meters per second squared. Okay, now that we have that, we can multiply it by the mass, which was 1,080 kilograms, right, giving us our 1.98 newtons times 10 to the 3 newtons. Yeah. Okay, any others? Oh, 7. Okay, so in number 7, we have a net force. So they tell us what F net is. Okay, 6.6 newtons east. Okay, mass is 9.0 kilograms. And then it accelerates uniformly from rest to 3 meters per second east. Okay, how far did the object travel? Okay, so I have the net force and I have the mass. What can I calculate with that? Acceleration. I can calculate the acceleration. All right, so I'm going to do that. I'm going to say acceleration equals F net divided by m. Okay, so that'll be 6.6 divided by 9. All right, so I've got an acceleration of 0.73 meters per second squared east. Okay, and I know it's east because this force was directed east, and acceleration and force are always in the same direction. Now that I have that, I have one more piece of the acceleration puzzle. Now I can calculate d, but I have to use this formula to do it. Okay, because I have d, I have vi, I have vf. Okay, I'm just manipulating, okay, for d, so vf squared minus vi squared over 2a equals d. So 3 squared minus 0 squared divided by 2 times 0.73. Okay, and that should give us our displacement of 6.1 meters. Okay, and then once I have that, I can use any of the acceleration formulas I want to calculate t. Or I could have gone the other way and got
double. Did you like maybe not times it by 2?
You did the 9 divided by 6.6 when you were doing your answer key.
I did?
Yeah. So it's
Whoops. Okay. Is it that answer on your sheet?
yeah, it's that answer on our sheet, but it's like the correct answer is what you just did.
Is what I just did.
Yeah.
So I did it right here.
You did it right here.
Okay. Well, at least I did it right here. It would be embarrassing if I didn't do it right here. Okay. All right. Yeah. So, and then yeah, like I say, from there we can use any acceleration formula we want. I will go back and change that key so that it reads correct now. So. Are you sure? Because I just got the same number.
I think it's
Yeah.
Like maybe I've done it
I see
right.
an issue.
I've done it right twice now.
I got that.
Okay, here's what I think's happening.
I'm
Are you
getting
enclosing
3.6.
this in brackets
Yeah,
on your calculator?
I did.
Remember to square the 3?
Yeah.
Then I don't know how you don't get 6.1.
Like I was getting time right too.
Yeah, I was getting time right. I was just getting like half for some reason.
Half the distance.
Yeah.
Feels like you're not multiplying this by 2. Here's what I think is happening. If you don't put this in brackets, it goes 9 divided by 2 and then multiplies by 0.73, which is not the same as dividing 3 squared by 2 times 0.73. You have to do it in that order. If you don't enclose that in brackets, yeah, you're probably going to get that other answer. Let's test that out. I get 3.3 now. I wish I could replicate what you're doing. Except that it's wrong. But,
Yeah,
but,
I get 3.3.
yeah. So remembering to square and put it in brackets. And you're using that formula? Weird. Can I see what you're doing? Okay, guys, if I can get everybody's attention up here for number 10, because number 10 is a great question, because it's one that it's kind of an example I told you about the other day when we were talking about elevator questions, and I said, if I word this question this way, people will forget it's an elevator, right? So I have this object that's thrown vertically into the air, okay? If I throw something vertically, how many forces are acting on it? 2. The applied force of the throw and gravity. But when I say I've thrown something in the air, people forget about the force of gravity. Okay? If I say this is an elevator, they remember gravity. Okay? If I say I throw it up in the air, suddenly it's magical and all it is me throwing it. Okay? So we have to remember that that's the case here. Now it tells me that the initial acceleration, which is the net acceleration, is 8.80 meters per second squared. Right? Since I know the acceleration and the mass right off the bat, I can calculate F net. Okay, so I'm just going to take my 15 kilograms and multiply that by the 8.8, and that'll give me my net force. Okay, so we got 132 newtons. That's my net force. Okay, they want to know the applied force, this one. Well, then I have to remember that the other way to calculate net force is the vector sum of all forces. Okay, Fa plus Fg. Now, can I calculate Fg here as well? Right, calculate gravity, mass times acceleration due to gravity. All right, so what we have is that 132, or sorry, we'll manipulate it. We're looking for Fa, so I'm going to subtract Fg over to the other side. So we'll have F net minus Fg equals Fa. All right, when we plug in our numbers for that, we're going to have 132 newtons up, so that's positive, minus our force of gravity, which I haven't calculated yet. Okay, 147.15, but that's negative because it's down. All right, so my applied force is going to be the sum of these two numbers. Okay, so my applied force is 2.8 times 10 to the 2 newtons up, or maybe it's 279. I don't remember how many significant digits were in that answer. Okay, 279 newtons. And that should be up. That needs to have a direction on it because it's a vector. Okay. Any other ones? All right. I'm going to give you guys about a 5-minute break. Let's come back here 10:50. Okay, and I'm going to go over the pulleys. The pulley stuff. Okay. So 10:50. We're back here. We're talking about pulleys. All right. So the other day we were talking about systems. Okay, and we said that in a system, all parts of the system have to have the same magnitude of acceleration. They do not, however, have to have the same direction of acceleration. A device like a pulley can distribute the force between the objects, still allow them to both accelerate at the same rate, but it can redirect that force so that one of them accelerates in a different direction than the other. Case in point, these two masses hanging over a vertical pulley. One of them is going to accelerate down. The other is going to accelerate up. But the magnitude of those accelerations will be equal because they're connected. Okay? One is pulling the other. Or they're both pulling each other. Okay? Everybody with me so far? All right? Now, which way is this pulley going to go? Right, the 35 is going to drop and the 25 is going to go up, right? The heavier object is the one that's going to fall. Now, it's vertical. Will it fall at 9.81 meters per second squared? No, it won't. Because the force of gravity is acting in opposition to itself. It's pulling on both masses, and they're in opposite directions. Okay? I mean, it's pulling both down, but one of them isn't going to move down. All right, so here's what we got to do with this. We have to do what we did with the very first system we looked at. We said, all right, there's forces acting in this system, and we're going to identify them. Those forces are the force of gravity, okay, which in this case is going to be 35 times 9.81, so 343.35 newtons. Okay, and the other force is what? It's a trick. It's the force of gravity. But it's acting on the other mass. Those are the two forces. Okay? Gravity is pulling on both masses. Right? It's just going to create a net force in the direction of the 35 kilogram mass instead. Right? So we'll have this force of gravity here, okay, be 245 point something. 25 times 9.81. 245.25. Okay. So gravity is pulling downwards, but these two things are connected over a rotating pulley, which will redirect the forces. So really, what I can do here is simplify this. how much mass is being accelerated here?
Kilograms.
60 kilograms. I don't want to subtract them, I want to add them, right? The whole mass of the system is being accelerated. Both boxes have got to move, right? Both of these masses have to move. So I've got a 60 kilogram system being pulled one way by 343.35 newtons and resisted the other way by 245.25 newtons. Okay, that's really what's going on here, right? I've got two different masses, they're both hanging over a vertical pulley. If I let it go, the 35 kilogram mass is going to fall, the 25 kilogram mass is going to move up, and they're going to do it at the same rate because they're attached by a rope. Okay? So this is just like the first one that we had with the two masses that we just added together, the 10 and the 20 boxes on the sliding surface. All right, can I calculate my net force?
Yeah.
Yep. Okay, so F net's going to be 343.35 minus 245.25 for 98.1 newtons. Right, so my net force will be 98.1 newtons this way, okay, towards the 35 kilogram mass. Okay. Can I calculate the acceleration now? Right. Okay, so I can go acceleration equals F net over m. Right? 98.1 divided by 60 kilograms. All right. Whoop, not times. Divided. Divided by 60. Okay, 1.6, and we only have two significant figures here, so 1.6 meters per second squared is the acceleration of the system. It asked, what's the acceleration of each object? How is that going to be different? The directions. So I would have to say here, the acceleration of the 35 kilogram mass is 1.6 meters per second squared down. The acceleration of the 25 kilogram mass is 1.6 meters per second squared up. Right? Works just the same as those two sliding masses attached by a rope. These are masses attached by a rope. It's just over a pulley. Okay? Our two forces are the force of gravity acting on each one. Obviously, the heavier one is the one that's going to be the one doing the driving. Okay? And the lighter one is going to be the one doing the resisting. Okay. All right. Everyone kind of follow how we did that. All right. So this works the same regardless of how the pulley is set up. We're going to be doing a lab where we're going to have one of those carts we have on the track with a pulley on the end of the track. And we're going to hang masses over the pulley, and we're going to allow the masses to pull the cart. Okay? Gravity is going to act as our applied force. Okay? Gravity is just going to pull the hanging masses over the pulley down to the floor, which will indirectly pull on the cart, okay? Causing it to accelerate. You all right with that idea? So, could work something like this. You guys could give this one a try. Okay? We have these two pails, so they're saying that pail B, which is this side here, is 8.0 kilograms. Okay? And this one here is 6.0 kilograms. Right? And the tire is 20 kilograms. Right, so calculate the magnitude of the acceleration of the system. Okay, notice they just said magnitude because if they ask about the system, that's all you can give because every part of this system has a different direction. So first thing we have to do is kind of complete the free body diagram here and identify the forces that are acting in this system. So we're going to have a force of gravity pulling on the 6 kilogram pail. That'll be 58.86 newtons. Okay, 6 times 9.81. Right, and then we're going to have a force of gravity here, okay, acting on the 8 kilogram one, 78.48 newtons. Okay, there. right, where there's no friction on the table, right? Even though in the real world there probably would be, okay? There's no friction on the table, so these are my only two forces, right? Now I need to put this whole system together because the whole system is going to accelerate together, so I'm simply going to simplify my diagram, right? I am going to have 34 kilograms worth of mass, 20 plus 8 plus 6, okay, for a total of 34 kilograms worth of mass, being pulled this direction by 58.86 newtons, and this direction by 78.48 newtons. Right. What can I calculate right now? I can calculate my net force. All right, so F net is the vector sum of all forces, so that'll be 78.48 minus 58.86, which is 19.62 newtons. All right, going this direction, in the direction of the 8 kilogram pail, okay, is going to be our direction. Now, it only asked, what's the acceleration? So all I have to do now is take my 19.62 and plug it in here. F net divided by mass. Right? That'll be 19.62 divided by 34 kilograms.
Wait, the mass is 34.
Yep, because it's the whole system, right? It's the tire and the two pails.
Okay.
Yeah. All right, so we're going to have 0.58 meters per second. And that's all we can write because they wanted the acceleration of the system. 0.58 meters per second squared is all we can give because all the parts of the system have different vectors to that acceleration. Right? Now, if it were me asking this question, I would probably ask you, what is the acceleration of the tire? Okay? In the hopes that I could catch some people not giving me a direction, or dividing 19.62 by the mass of the tire and not the mass of the entire system. Okay, that's what that question would be checking. Okay, do you remember that when we're talking about a system, we have to find the acceleration of the entire system. Okay, all of the mass goes together.
So that would just be the same acceleration to
Yep, exactly. It would still be 0.58 meters per second squared left. If it were talking about the 6 kilogram bucket, it would be up. All right, questions on that? Okay. That's all the same stuff. Okay, we're not going to get the static stuff today. So, back on this worksheet here, I know you guys have been working pretty hard on this one. Okay, I want you guys to try a couple of specific ones here. Okay, I would like you guys to do 16 through 19 for right now. Okay, 16 through 19. Actually, sorry, 16 through 20, because that one's got the vertical pulley. Okay, 20's got the vertical pulley. Okay, so on number 18 here, it says we're traveling in our car at 24 meters per second east. Okay, when you slam on your brakes. Okay, the force of friction on your car's tires is 1.8 times 10 to the 4 newtons, or 18,000 newtons. Okay, if the mass of you and your car is 1,500 kilograms, okay, how far do you skid before stopping? All right, so we're looking for distance here, and because they said stop, we know that VF is 0. Okay, so now what I got to look at is this from a forces point of view. Okay, free body diagram. Okay, there's my car, 1,500 kilograms. Okay, what forces are acting on the car? Gravity. What else? Normal force. And how are those two forces related? Right, they cancel each other out, right? They're there, but they're equal and opposite, so I don't need to worry about them in terms of a net force calculation. What's the other force? Friction. Yeah, the brakes, right? All right, since these two forces cancel each other off, that force is also then by default my net force, which is true anytime you have a car slamming on its brakes on a level surface. Okay? Once you slam on the brakes, the engine isn't pushing you forward anymore. Right? Only friction is causing you to accelerate or slow down, decelerate. Okay? So that is now my net force. Since now I know that's my net force and I have the mass, I can calculate the acceleration. Right? So acceleration will be 18,000 newtons, my net force, divided by 1,500 kilograms, my mass. Okay, so 18,000 divided by 1,500, that gives us 12. All right, so my acceleration is going to be negative 12 meters per second squared, or 12 meters per second squared west. How do I know that? Right, because the car's traveling east. Okay, my brakes have to produce an acceleration opposite to east, so it's west. Now, I can calculate how far it travels using this formula. Vf squared equals Vi squared plus 2AD, just solving for D. So D will equal Vf squared minus Vi squared over 2A. Okay, and so that's going to be 0 squared minus 24 squared divided by 2 times negative 12. Okay, it's key that I make that 12 negative because I've got a negative on the top as well. Okay, so I'm going to have 0 minus 24 squared, gives me that, divided by, whoa. Okay, stop it. Okay, then divided by a negative 24. Okay. So there we go. Gives 24 squared. Yeah. Everybody all right with that? Okay. So we're going to travel 24 meters, okay, before coming to a stop. Okay, everybody all right with that? Everyone's good there? Okay. Any other ones giving us trouble there between 16 and 20? 16? No. Okay, so in number 16, we've got a 1 kilogram object that's given a push along a horizontal surface. The velocity of the object when it's released is 0.50 meters per second west. All right, so VI 0.5 meters per second, oh, not squared, west. Okay, the object slides 0.25 meters, okay, before coming to a stop. What is the magnitude of the force of friction? Okay, so if I'm looking at this, once I push an object, okay, so if the object is this brush, okay, if I give that a push, once I'm done pushing, what's the only force acting on it that matters? Friction. It's just like the slamming on the brakes question. Okay, it's the force of friction that's going to bring it to a stop. It's the force of friction that's going to be my net force, okay? Because gravity and normal force are going to cancel out. All right, so I'm going to have this 1 kilogram object, okay, and I know that the only force acting on it is the force of friction, and that force of friction is my net force. So if I want to calculate, so what I did right there is the vector sum of all forces. Okay, there was only one, so I'm done that part. Right, now F net equals m times a. Right, so I need acceleration, which I can get from this formula. Okay, acceleration is Vf squared minus Vi squared over 2d. Okay, so we'll have, where are our numbers here? 0.5 and 0.25. So and divide by 2 times 0.25, and we're going to get 1, right? No. Hang Yeah. 0.5 meters. Okay. Everybody all right with that? All right. Any other ones? How many people are done all the way to 20? Okay, number 21 is an elevator question. So is number 22. So if you're done up to number 20, give 21 and 22 a try. Okay, the bathroom scale is reading the upward force. Okay, it's reading the force of the floor pushing on their feet. Okay, so it's equivalent to that upward force of the cable that we were talking about the other day. Okay, so whatever the scale reads is the upward force the elevator is applying. Right? What's the downward force? Gravity. Okay, give those two a try. Okay, so we have a 725 Newton student. That's their weight. That's the force of gravity. Okay, if they tell you that somebody has this many newtons, that's their weight, that's the force of gravity. So we know Fg is 725 newtons. Okay, we know that when they're on the scale and the elevator begins to rise, the upward force, which we call the normal force, is 775 newtons. Okay, so they feel heavier than normal. So we want to find the acceleration of the elevator as it begins to rise. All right, so right now I can draw the free body diagram. 775 newtons. Okay, and I can draw this 725 newtons. Okay, that's Fg. That's F normal. What do I not have? Mass. Okay, but if I remember, this is how I calculate the force of gravity. Right? So all I have to do is take the 725 and divide by 9.81, and I'll have the mass, and then it's just a matter of net force, 50 newtons, divided by the mass. Okay, and that's where we'll get that 0.677 meters per second squared up. From. All right, you will have a quiz on Newton's second law tomorrow. Expect probably an elevator question and something simple like you started the class with. Okay, expect that that's probably what you'll see tomorrow. I will post something before the end of the day. All right, let's get those desks wiped down.
I told him